Okay, so this revision video is about generators and how they work. And the first thing we need to understand, a bit like with the motors, is something called the generator effect. So this is where you have a wire and you move it through a magnetic field, and you move it in such a way that it cuts through the lines of magnetic field. So if we put our wire here and we move it downwards through the magnetic field, what we do is we induce a voltage across the wire. And what that does is it means that if the wire forms part of a closed loop, then current will flow. So the arrow on this wire shows the direction that current would flow in if the wire was part of a closed loop. So once again, we have a wire which we're moving through the magnetic field, which is inducing a voltage. And exactly the same as with the motor effect, if we were to switch either the poles of the magnet round to reverse the direction of the magnetic field, or we were to move the wire up instead of down, then we would reverse the direction of the induced voltage in that wire. The second way to think about it, of course, is the fact that because we have to cut through the field lines, if we look at this wire here, we're now moving it along the field lines. Because it's not cutting through any, it won't induce any voltage. So the motion shown here with the wire moving along the field lines does not induce a voltage in the wire because we're not cutting through the field lines. Okay, the alternative approach to thinking about how a generator works is the idea that we need this motion, but we don't really care whether actually it's the wire moving or the magnet moving. So as long as there's motion between the two of them relative to each other, then we'll still get a generator effect. So this version of the explanation works better actually when you've got coils of wire, and you have what we're doing here is we're taking a magnet and we are dropping it through a coil of wire that is attached to a voltmeter here. So the voltmeter is going to tell us what the induced voltage is in this coil of wire due to the passage of the magnet. And the way to think about this is that you will induce a voltage in the coil of wire if you have a changing magnetic field in the coil. So as the magnet drops into the coil, it increases the magnetic field in the coil, and as it drops out, it decreases it. And what we have then is this graph on the right hand side is I'm going to plot the voltage over time as the magnet drops through the coil. So here we go. So it drops through. As it drops in, there's a voltage peak in one direction. As it drops out, there's a voltage peak in the opposite direction. Okay? So that's due to the changing magnetic field in the coil. When the magnet is sat inside the coil here in the middle part, there's not really much voltage induced because although it's still falling, then there's not very much changing magnetic field in the coil. It's pretty much constant. It only really changes as the magnet moves in and as the magnet moves out. Okay, so those are our two ways of thinking about inducing a voltage in a coil of wire. And by the way, this approach, this magnet falling through the coil thing, is exactly the same thing as you get when you get those torches that you have to shake to recharge. You're inducing a voltage in a coil, and the thing that's wobbling up and down the torch is a little magnet. Okay, so in summary then, the two pictures for the generator effect are we need motion of a wire relative to a magnetic field, provided the wire cuts the field lines. That will induce a voltage across the wire, and that process is called electromagnetic induction. And that will lead to a current flowing if the wire is part of a closed loop. So you can induce a voltage without having a current flowing. Okay, that's important to realise. The current will flow if the wire is part of a complete circuit. And the other way to think about it is the changing magnetic field in a coil of wire again will induce a voltage, and the same thing, we'll get a current flowing if the coil is part of a closed loop. So those are the kind of two pictures two different ways we can think about the generator effect. And you might pick one or the other depending on what situation you've got. If you've got a wire cutting through a magnetic field on its own, then probably the top one. If you've got a magnet moving relative to a coil of wire, then probably the bottom one. Okay, so how does this work with a real generator in principle? Well, we're going to look at the idea of the coil of wire rotating in the magnetic field of the generator, though in reality most generators rotate the magnet. But again, we've said it doesn't really matter which one is moving as long as they are moving relative to each other. And this explanation kind of meshes a little bit with our motor explanation, so this is the one we're going to use. So it looks very similar to the motor. The key differences, though, are the fact that we've still got the graphite brushes. We have this, instead of a cell here, we've got this load resistor, because remember the whole point with the generator is we're trying to produce a voltage and therefore electric current, so we don't need to provide one here. And this load could be anything. It could be a bulb, it could be a motor, though that'd be a bit pointless. Anything that you can, any circuit component is fine. And then instead of the split ring commutator we had in the motor, we've now got slip rings, which do one of the jobs that the commutator did, but not the other one. They allow the coil to rotate, right? So, because remember in this one you are putting the rotation in, you are somehow driving this round. But they don't do the swapping of the sides of the coil, and that's important because it affects the output that we get from the generator. Okay, so like I said, something, if it's a power station, it'll be a turbine, causes the generator coil or the magnet to rotate, and then we can see from our explanation that the wires in the rotating coil will cut through the field lines, inducing a voltage, or if you prefer, the rotating magnet, if we're thinking about the version where the magnet rotates, not the coil, the rotating magnet causes a changing magnetic field in the coil, and that induces a voltage. So that's the general principle. You will be required, though, to think about exactly what the output voltage looks like and compare it to the position of the coil at a particular time. So what I'm going to go through now is step by step in 90-degree sections what the voltage output looks like depending on what the coil position is. So again, we've gone to an end-on view of the rotation, and I've changed the colour very slightly of one of the coils so that we can keep track of where it is. And the little arrows on there are not representing force this time like they did in the motor video. These are representing the direction that that wire is moving in. And this is going to be important because we're going to get both those situations we talked about at the start. We're going to get some situations where the wires are cutting through the field and their field lines, and therefore we'll actually get a voltage, and we'll get some situations where the wires are moving along the field lines and we won't get a voltage. So that's how we're going to consider this, okay? So in this situation here, we can see that the wires are moving at right angles to the magnetic field, so they will be cutting through the magnetic field. So we're going to plot a point on our graph that is a voltage. We've induced one. I'm going to call it a positive voltage, pointing one way in the circuit. I'm going to label the point with what the coils look like at that position so that we can actually see as we go along what the progression is, okay? Right, so then we're going to rotate round 90 degrees, and now if we do that, we can see that the coils are moving parallel to the magnetic field now at this point in time. In other words, at this particular point, they are moving along the magnetic field lines, and we said that when they're moving along the magnetic field lines, they don't induce any voltage at all. So we've got this position on the graph. Okay, another 90-degree rotation, and they are back to cutting through the field lines. But the important point is here, if we compare this situation to the first one here, the wires are swapped round, and what that means is, just like in the motor, that if we didn't swap them back with a commutator, which we're not doing here, then the voltage we induce here will be in the opposite direction, just like the motion would have been, or the force, sorry, would have been in the opposite direction in the motor if we hadn't swapped them round with the split ring commutator. So because the wires are swapped, the voltage we are inducing is pushing the other way in the wires, and we call that negative voltage. It's pushing back the other way. Another 90-degree rotation, we're back to along the field lines again, and because it's 0, we don't care which way round the coils are, 0 is 0. And then we just keep going, so we get back to our original situation now. If you look, we're back matched up to our original situation, so we will get our original voltage back again. And that cycle will just continue, and I'll continue it for one more step so you can see. Right, and then the output voltage when we join those points up looks like this. Okay, it's a sine wave, and it's we call that alternating current. Okay, or rather, it's an alternating voltage which will produce alternating current in a complete circuit. So that's what the output for a generator looks like, and you'd be expected to be able to label coil positions on the graph like this. Very often, they will give you one to start with. So you might not have to remember about the wires cutting through the field lines as to which, to tell you whether you've got a high voltage, a 0, or opposite voltage. All you need to remember if you get given one of these positions is that each 90-degree rotation, right, brings you from a 0 to a minimum, or a minimum to a 0, or a 0 to a maximum. So if you remember the positions of those points, and you remember that the journey between each point is a 90-degree rotation, you can then do the relative positions of the coil. Okay? So this is really important because if you think about power stations, the first thing the generator is attached to after the it's attached to the turbine, and then the generator, and then a transformer. And transformers only work with alternating current. So this is the reason we don't bother with the split ring commutator in the generator. We want an alternating current so that our transformers will work. Okay? If we did put the split ring commutator in, all it would do was sort of fold up these negative parts of the graph into the positive. It would just fold it, okay? And so we'd still have the bumps, but they'd all be at positive voltage. And that's not particularly useful, so we don't do that. We leave it as alternating current. Okay, other things you need to know. Oh yes, worth remembering that one complete cycle of this rotation, of course, one complete cycle of the AC is a 360-degree rotation of the coil. Also worth remembering that for the national grid, the rate of cycling is 50 times per second, or 50 hertz, and that means each one of these cycles is 0.02 seconds long. So from this position here, where we have the coils in our original position, back to when they're in their original position again, takes 0.02 seconds. Okay? Right. How can we increase the voltage produced by a generator? Well, this is very similar to the list of things for increasing the force on a motor. Stronger magnets on there again. Multiple turns of wire in the coil on there again, because each one will have a voltage induced across it. And when you put multiple coils of wire in your generator, it's like putting multiple cells in a row. You add up the voltages from them. Okay, iron core inside the coil to concentrate the magnetic field again. And finally, what we have here, which we didn't have for the motor, obviously, is rotate faster. If we rotate the generator faster, the coils will cut through the field lines faster, and so you will induce more voltage. It's also worth being able to talk about that graphically. So what does the output look like if we make those changes? So if we have our original output from our generator, we're just spinning it at some rate, and it's got a magnet in there, and it's got a particular number of coils. What would it look like? The first one we're going to do is if we double the number of coils, or if we double the strength of the magnet. Well, all that happens, right, is the time it takes to do one rotation stays exactly the same, and all that happens is the height of this oscillation doubles. So in other words, the amplitude of this increases. So if we were peaked at, say, 5 volts on the top graph, we'd be peaked at 10 volts on the bottom graph if we double the magnet strength or double the number of coils. If you put the iron core in there, it would look like that. It would increase, but it wouldn't necessarily be doubled. Okay, so if you're asked what it looks like when you put if you've got a generator and you put an iron core into it, all you would have to do was to draw the same pattern, but with a larger amplitude, so a larger peak voltage. Okay, on both sides of the line, peak higher voltage, so plus 10 in this case, and minus 10 on the other side as well. So that's 3 of the things from our list. The thing that's a little bit different is the rotation speed. Okay, so if we look at that now, get our original output back again. The rotation speed, if we double that, it does 2 things. It does the same thing as the previous graph by doubling the peak voltage. But also, if you think about it, doubling the rotation speed means each cycle will be half the length. So when we double the rotation speed, the graph will look like this. You'll fit 2 complete cycles in where you previously had 1 complete cycle. Okay, that's it.